So today we will see some examples of direct sum of subspaces. Direct sum, okay? So some examples. So for example, in R2 we are again going to consider another example. Suppose B is R2 and W1 is a subspace spanned by the single vector 1, 1. So what is the linear span of a single vector 1, 1? That will be like this: A, comma A, such that A is in R, isn't it? Because there is only one vector, that is 1, 1. So the what will be the scalar multiple? That is the you multiply by a scalar A. So each and every component will be multiplied. So A, comma A. Similarly, suppose W2 is also a subspace spanned by another single vector. Let us call this 1, 2. Then what will be the linear span of this set? Because there is only one vector. So you just multiply, take all the scalar multiples of this vector. So it will be like this: B, 2B, such that B belongs to R. Right? Then we claim that R2 is the direct sum of these two subspaces. Okay? Why? Because if you observe in Cartesian coordinate system, so this is your x-axis, this is your y-axis for moment, and this is your origin. So let us consider where is W1. So W1 means this is the point 1, 1. Okay, this one. Okay. So the line passing through this, all the scalar multiple of 1 means if you take 0, then will be 0 vector. If you take 1, 1 vector. If you take 2, 2 vector, and so on. Is not it? So this infinitely extendable. So this line, if you take negative of that, so this line. So this line is the W1. Okay. So this is W1. Similarly, if you take 1, 2. So here at 1, this is here. Yeah. This is 1. This is suppose 2. So this point is 1, 2. This point is 1, 2. Okay. 1, 2. Sorry for that. Yeah. 2. So the line passing through this. So take all the scalar multiple of 1, 2. So if you take the 0 vector, so you just multiply this. Okay. So all the scalar multiples. So these are actually lines, is not it? So this is your W2. Now you can see if you take any vector, suppose, sorry, let xy is any vector, x comma y is any vector in R2, then what you see? You see that x comma y can be written as linear combination of these vectors. That is the sum of these two vectors. One is W1, one is from W1, and another one is from W2. So this vector, if you consider this one and this one, so xy can be written as some scalar multiple of 1, 1, because any vector in W1 is of this form. Similarly, any vector in W2 is of this form, B1, 2, where A and B are appropriate scalars. So just to solve this, you will get x comma y is equal to A plus B comma A plus 2. Is that it? So what you have? You have that A plus B is x and A plus 2B is y. I'm sorry, A plus 2B is y. So solving this, you will get B is equal to y minus x and A is equal to 2x minus y. Because x and y are real numbers, so A and B are real numbers. And therefore, R2, therefore every vector of R2 can be written as a linear combination of these two vectors. In other words, every vector of R2 can be written as one vector from W1 and another vector from W2. So we have actually proved that R2 is a subset of W1 plus W2, because this vector is from W1 and this vector is from W2. So what we have shown? We have shown that every vector of R2 can be written as one vector from W1 and another from vector from W2. And therefore, R2 is contained in W1 plus W2. Okay? And this is clear. What is clear? And you know very well, just wait. Yeah, let us continue. So, because W1 plus W2 is a subspace of R2, so it cannot be bigger than R2. So, only the possibility is R2 is equal to W1 plus W2. Okay. And this is also clear that W1 intersection W2 is equal to the zero vector. Only the origin is there. You see from the picture, is not it? And second thing, what I have done here, suppose this is the vector x comma y. So how will you get this vector? You just draw the line parallel to W2 and you draw the line parallel to W1. You see? So parallelogram law is satisfied. So the vector sum is given by the parallelogram law, is not it? So I am not saying that this is just 1, 2. So if this is the vector 1, 2 and this is the vector 1, 1, of course this is the vector x, y, means this will be just sum of these two, that is 2 comma 3. So this vector is 2 comma 3. So in arbitrary way, if you take x, y any point in R2, you always can construct a parallelogram in which one is parallel to W2, another one is parallel to W1. And therefore, the vector is given by the scalar multiple of 1, 1 plus scalar multiple of 1, 2. So picturally, it's also clear, and analytically, we have shown that R2 is just W1 plus W2 with W1 intersection W2 is 0. And therefore, what we have shown? We have shown that R2 is W1 direct sum W2. So I hope it is clear to everyone. Is it okay? Write in your chat box clear this example to everyone. B is equal to x minus a होगा. B is equal to x minus a होगा. What is B is equal to x minus a होगा means? या x माइनस ए आएगा, लेकिन हमको तो x और y के टर्म में a और b की वैल्यू निकालनी थी ना, so that's why we have done like this. Okay, fine. Good. Let us see another example. Okay, let us continue. So let us take another example, and now this example, before this example, let me clarify. So clarify is that indeed what we have done, indeed next page. Indeed, if W1 and W2 are two lines, distinct lines in R2, of course passing through origin, then R2 is always the direct sum of these two subspaces, these two lines, W1 plus W2. Okay. So picturally, suppose this is the x-axis, the y-axis, and this is your x-axis, right? And this is your origin. And suppose this W1 is any line, of course, passing through origin. Okay, passing through origin. I'm sorry for that. This is your W1. So any line passing through origin is a subspace of R2. So this is a subspace of R2. Similarly, suppose W2 is another point. W2 is another line. Okay. Suppose W2 is another line. This is W2. So this is also a subspace passing through origin. So what you see, if you take any point, say here, you are taking the vector B, then what you see? Just draw the line parallel to W1 from B and project on W2. Similarly, draw a line parallel to W2 from B and project at W1. So what you see, this is a parallelogram, is not it? This is a parallelogram. Okay. So this part, up to this part, it is some vector W2. And up to this part, it is some vector, say, W1. Okay. And therefore, we can always be written as W1 plus the direct sum of this. So this is W2. Right? So what do you see? You see that every vector V in R2 can be written as one vector from W1 and the vector from W2. And it is clear that W1 intersection W2 is nothing but only the zero vector. And therefore, R2 is here direct sum of these two, that is W1 plus W2, is not it? So you write in this thing, that is, if W1 and W2 are any two lines, of course, distinct lines. So it is better to write distinct lines through origin. In R2, then this R2 is the direct sum of these two, that is W1 plus W2. So basically, in abstract vector space, we can define, whenever we will mean the line through a vector V, we will understand that all the scalar multiple of V. So let me define this. Okay. Let me define this. Given a vector V which is non-zero, the set of all scalar multiples of V is called the line through V. Of course, which passes through zero vector. Because you are considering all the scalar multiples, so automatically when you multiply by 0 to any vector, it will be the zero vector. So obviously it will pass through the zero vector. So in abstract vector space, whenever we talk about that, a line through a non-zero vector V, that means we are considering all the scalar multiples of the vector V. So that means this is a subspace. Okay, that is, a line is a subspace. Of course, passing through origin, a line is a subspace, which is obvious. So let me ask you a combinatorial question. What is the combinatorial question? So combinatorial question is like this: how many lines are there in finite vector space? Which one? Namely ZPN. How many lines are there in ZPN. What do you mean by ZPN? This is nothing but the direct product of ZP cross ZP cross ZP. So this is the direct product of ZP n times. Okay, and so on ZP. And what is ZP? Where P is a prime. So you know ZP is a field, the set of residue classes modulo P. So this is a field. So every field is a vector space over itself. So that's why, and you know direct product of vector spaces is again a vector space. So this is also a vector space over ZP. So here F is ZP and V is ZPN. So this is obvious because ZP is a finite field. So ZP cross ZP cross ZP, how many elements are there? So obviously any element in this set is of this type. A1, A2, dot dot AN. Okay. And the elements are from ZP. And you know ZP means the set of residue clauses modulo P. So 0 bar, 1 bar, 2 bar, and so on, P minus 1. So there are P elements. So every coordinate can be taken in P ways. So how many elements? So the first answer, so first we answer the number of elements in this vector space. So actually this is a finite vector space. That means number of vectors are finite. So how many elements are here? So the number of elements are, so the number of vectors. So number of vector means you have n tuples of scalars. Scalars are from ZP. So the first coordinate can be filled, can be taken in P ways because you can put here 0 bar, 1 bar, 2 bar, or P minus 1 bar. So the first place can be filled in P ways. Similarly, the second place also can be filled in P ways, and so on. So the last place also can be filled in P ways. So how many places are here? So there are n places. So this is n times. And therefore, this is P to the power n. So this is just a counting principle. Okay. So this is the multiplication, principle of multiplication. Okay. So this is the principle of multiplication. So you might have studied about permutation and combination. So in the chapter of permutation and combination, there are two principles. One is principle of multiplication. Another one is principle of addition. Okay. So you go through that, you will learn a lot. Okay. So number of elements are finite. So obviously, question is how many lines are there? Okay. So let us suppose that there are only X lines. Okay. Suppose now we are going to answer the given question. Okay. So main question was that how many lines are here? So the number of lines is suppose X. Okay. Fine. And how many non-zero scalars? The number of non-zero scalars are P minus 1. Okay. So how many total vectors are there in ZPN? Let me ask you. How many non-zero vectors are here in this vector space? Means you have to exclude the zero vector because there are P to the power n vectors. So total number of non-zero vectors are P to the power n minus 1. Okay, fine. Now suppose that X is the total number of lines. Total number of lines means the scalar multiple of all the non-zero vectors. So suppose the total number of lines field, ZP is a field, then product of two non-zero elements is non-zero. Okay, because ZP is a field, in the field you know the product of A into B is 0 if and only if either A is 0 or B is 0. So how many scalars are there which is non-zero? P minus 1. And how many lines? There are X lines. In each line, how many elements are there? P minus 1 element which is non-zero. So total number of non-zero element is, in other words, X into P minus 1. So X into P minus 1 must be P to the power n minus 1. Okay. And therefore, the number, and what is X? X is the number of lines. Okay, so in this way, x is e to the power n minus 1 divided by p minus 1. Okay, so this is interesting. Yeah, let me ask you, is it okay? Clear to everyone? The last example, every field is a vector space over itself. So ZP is a vector space over itself. So ZP cross ZP cross ZP, direct product of vector space is again a vector space. So here the elements of B are n tuples of scalars, and scalars are from ZP, which is a prime field. Okay, having P elements only. So the first question is how many elements are there? Because it's a finite field. ZP is finite. So the finite product of finite set is finite. So the finite product of a finite set is finite. So it must be finite. So how many elements are there? Because for each scalar you have p choices. So how many choices? So for first you have p choice. For second you have p choice. For third you have p choice. Now corresponding to each choice there are p choice. So multiplication principle is applied here. So p into p n times. So p to the power n. So you now know how many elements are there. P to the power n elements. And you know there is one zero vector which is unique. So excluding that zero vector, how many non-zero vectors? P to the power n minus 1. Okay, fine. Now suppose that there are x lines, and by the definition of line which has been given above to this question is that for every non-zero vector we can define a line. So if x is the number of line, so corresponding to each line, how many non-zero vectors? So non-zero vector you will get if you multiply by non-zero scalars, is not it? Because every vector is here n tuple. So corresponding to every non-zero vector, you get non-zero vector if you multiply by non-zero. So how many non-zero scalar? P minus 1 scalar. So how many non-zero vector total? X into P minus 1. So that's why P to the power n minus 1 will be the same as X into P to the minus 1. And therefore X is P to the power n. Now some examples from matrices. So let us see one example from matrices. So suppose B is set of all m by n matrices over any field F. You can take here R or C or any finite field also. Suppose W1 is set of all matrices in m by n over F such that Aij is 0 for all I bigger than j. Okay, I bigger than j means row. What is this? So suppose this is the matrix. Okay, suppose this is A11, A12, and A13. It is A22, A21, A22, and A23. And suppose this is A31, A32, A33. So you know this is the first row, this is the second row, this is the third row. So you see I greater than j. I greater than j means the first is greater than second one. So you see here first is greater than. So this must be 0. This must be 0. A32 this must be 0, and this is not. So these matrices, such type of matrices are called upper triangular in the case of square matrix. Okay. So here we are not considering square matrices, but meaning is the same. Okay. So if this row is not here, suppose this row is not here, the meaning is this. Means whenever the row is bigger than column, that element must be 0. So this is the structure. Okay, fine. Similarly, W2 is A belongs to m by n over F such that Aij is 0 for all I less than or equal to j. Just reverse of that. If you see, these are the complementary, right? This is the complement of this. Means the elements which are here 0, here may not be 0. The elements which are here non-zero, definitely here 0. Okay. So in first, the elements which are non-zero, in W2, the elements are 0. In a vice versa. The elements which are non-zero in W2, definitely in W1 are. So then you can see that the direct sum of these two, W1, W2 is m by n over m. This is the whole vector space. Okay, because W1 intersection W2 is 0, is obvious. The m by n matrix. You can see. If you take the common of these two, what will be that? That is Aij is 0 for all I is equal to uh, uh, means yeah. If you see the common vector, so common vector is only the 0 vector, because for the 0 vector W1 is subspace, W2 is subspace, so uh, both are having the 0 vector, so 0 vector must be there, so no doubt. But only 0 vector, how you can say? Suppose in W1 intersection W2 you have a non-zero vector, then you will get a contradiction. From W1 you will see that Aij is greater than 0 for all ij, for all I greater than j, and from W2 you will see that for all I less than or equal to j0. So the only common vector will be the 0. Okay, but W1 plus W2 has been left. Okay, now suppose B is any matrix like this, Bij, m by n, and of course it is any matrix in this vector space. Then what you see? Bij can be written as Aij corresponding to 1 plus Aij corresponding to 2. Let us call the first matrix as 1 and the second matrix as A2, where this Aij corresponding to 1 is nothing but Bij for all I less than or equal to j, and Aij corresponding to 1 is 0 for all I bigger than j. Now you check that. This Aij corresponding to 1 belongs to W1 or not? Of course belongs to W1, because that is the condition. And Aij corresponding to 2 is Bij for all I bigger than j and equal to 0 for all I less than or equal to j. So what you see? You see that the second, that is A2 matrix, belongs to W2, right? So obviously you have written that, what you have written? That the matrix A1 belongs to W1, comma, the matrix A2 belongs to W2. And already you proved that W1 intersection W2 is 0 matrix, is not it? And therefore, we have proved that V is W1 direct sum W2. Okay? So, today I finish here.